Bismillahirrahmanirrahim. Assalamu alaikum students. Today our topic is the fundamental theorem for curls. So my topic is the fundamental theorem for curls. So it's our topic. This theorem is also called Stoke's theorem. It is also called Stoke's theorem. Now, it states, I'll write the statement. It states integral of curl of some vector field V, surface integral of this curve over some surface S is equal to the line integral of the vector field, closed line integral over the boundary of the surface, perimeter of the surface. Let me explain it. So V is some vector field. V is some vector field. V is a vector field, right? And this del cross V, it's called curl of V, right? This dA, you know it, I'm just repeating it. This dA is infinitesimal area. Pen. This is infinitesimal. Let me fix this first. It's not working. Okay, it is infinitesimal area, right? S is some surface. P is perimeter of the surface. For example, if I have some surface S, on that surface will have some boundary. This is the boundary or perimeter. boundary or perimeter P of the surface, right? Now what is dl? It is infinitesimal displacement. Now what is this theorem saying? It's saying if you have some vector field, right, then you calculate its curl. The curl of a vector is also a vector. Then you dot that curl with infinitesimal area. That means you will have some surface. You will divide that surface into small elements, dA, right? We know that uh, dA is represented by vector, and that vector is taken as normal to the surface. Now if the surface is open, you can take area vector perpendicular to surface either way, upward or downward. But if the surface is closed, in that case, area vector is to be taken as outward now. Now we have some surface, right? We divide that surface into small area elements dA, represent each area element by a vector dA, which is taken as perpendicular to the surface. Then we find the curl of the vector field, dot that curl with this area vector, then add those dot products. That means integrate over the whole surface S. That's my left hand side. Then this theorem says that will be equal to, what you do, you find this called line integral. You go along the boundary of the surface. That means this perimeter P. Go along this boundary, divide that boundary into infinitesimal displacement vectors dl, dot the vector field with the infinitesimal displacement at each piece, then add those dot products over the whole perimeter. But you have to go along this boundary full because it is a closed integral, right? So this is the statement of this particular theorem called Stokes theorem or fundamental theorem for curls. Now remember what is curl. Now we know this del, you are familiar with it. It is dou by dou x I cap is a vector operator plus dou by dou y j cap plus dou by dou z k cap. Now if I have some vector field v with components vx I cap plus vy j cap plus vz k cap, then the meaning of curl del cross v, you can evaluate that using this determinant I j k dou by dou x dou by dou y dou by dou z. This determinant you can solve vx vy bz. This way you can calculate the curl, right? Then there is one thing, when you evaluate this closed line integral, you have to specify your direction of travel, and dA is to be taken as perpendicular to the surface. Now it can be downward, it can be upward, perpendicular to the surface. Now which way we have to take, that is connected with the direction of travel, and for that we have a right hand rule. What's the right hand rule? If this is my boundary, this is my surface, this is my surface, and this is my boundary. If I move along the boundary while calculating my line integral, closed line integral, if I move in the finger of right hand, this in the sense of right hand fingers, then dA is to be taken in the direction of thumb of the right hand. It's called right hand rule. A right hand rule. It's right hand rule. When I have to evaluate this particular line integral over the closed boundary, if my direction of travel is sensed in the direction of fingers of right hand, in the direction of right hand fingers, then dA is to be taken along the thumb of right hand, right? So remember this. This is the relation between the direction of dA and the direction of travel while calculating the closed line integral on the right hand side of this theorem, right? One more thing you need to remember. If I have some boundary, same boundary can enclose many surfaces, infinitely many surfaces. I specify it by writing same boundary or perimeter can enclose infinitely many surface. This is important. Same boundary or perimeter can enclose infinitely many surface. What is the meaning of that? If I have this, let this be some piece of cloth, some rubber sheet. Now it has a boundary. Let the surface be flat. Then that is one surface. Now it is possible that you bend this surface. Still, the perimeter or boundary is same, but surface is different. Now you can bend this surface many ways. You can bend it like this. You can bend it like this. You can bend it some different way. In all cases, the perimeter or boundary of the surface is same, but surfaces are different. The surface 1, let it be S1, this is some other surface, this some other surface, this some other surface, right? Now, this is surface integral. When you divide some surface into little patches of area, then you dot some vector with that area vector and add those dot products over the surface. Such integral is called surface integral, or sometimes it is called flux of this vector. So this is flux of the curl of V through surfaces. Now such integrals normally depend on the surface. I am saying surface integrals normally depend on the surface for which they are calculated. But this fundamental theorem of curls is saying that this surface integral is equal to this thing, is equal to line integral, closed line integral along the boundary, and this boundary is unique for many surfaces. Right hand side is not specifying the surface, which surface we have to take into consideration. That means for these surface integrals of curls. It is immaterial which surface to take in calculation because of this theorem. So we have a corollary to this theorem. We have two corollaries. One corollary, corollary is byproduct of theorem. So corollary first, it is integral of the surface integral of curl of vector field depends only on the boundary line, that is perimeter boundary line, not on the particular surface used. I've already explained it. This one corollary, that surface integral of the curl of the vector field depends only on the boundary line, that's the perimeter, not on the particular surface used. This follows from this Stokes theorem. The second corollary, first I have to explain one thing. I am saying that if you have a boundary, now it encloses many surfaces. It is also one of the surfaces. Now if you make this closer surface, that means if you shrink the boundary, now this you are shrinking the boundary, this surface. If you shrink this boundary to point, if I shrink this boundary to point, what will happen? My surface will become closed. That means if I am shrinking the boundary to point, what will happen? The right hand side of Stokes theorem will become 0. This path will shrink to point. So second corollary will become, if this is a closed surface, my right hand side will be 0. So I have second corollary. So my corollary 2 of Stokes theorem, is closed integral of curl of V dot dA is 0 for any closed surface, for any closed surface, since the boundary line shrinks down to a point, and hence the right side of equation 1 vanishes. Equation 1 is the theorem. This is my equation 1. Right hand side becomes 0. So this was my second corollary, closed integral, surface integral of curl of V is 0 for any closed surface, since the boundary line shrinks down to a point, and hence the right side of equation 1 vanishes. Now this was the theorem. Now we will do an example. Example is like this. Simple. Example says, suppose V is equal to xz plus 3y square j cap plus 4y z square k cap. Right? Check Stoke's theorem for the square surface shown in figure 1. Now I will draw a figure. My figure is like this. X, Y, and Z. Now let the coordinate here be 1. Coordinate here be 1. This is my figure 1. Understand this question. It is saying suppose V is 2xz plus 3y square j cap plus 4y z square k cap. So we are given a vector field. This is y component of the vector field and it is its z component. Question is saying check Stokes theorem for this square surface shown in figure 1. Now in this figure we are given a square surface. It's a surface, right? On this side length is 1, on this side length is 1, the coordinate here is 1, here is 1. This square surface is placed in YZ plane. X is perpendicular to it. Now we have to check this theorem for this particular surface, right? That means we have to evaluate left hand side of the Stokes theorem, then we have to evaluate right hand side, then we have to check whether left hand side is equal to right hand side. Before doing this question, understand this is the boundary of this surface. I will shade it in order to understand it. This is your surface, right? So you have to decide for this surface the direction of area vector. We know area vector is to be taken as perpendicular to the surface. Now that area vector can be taken as perpendicular to the surface along positive x or downward along negative x, right? I said for that we have a right hand rule. We decide that while calculating the closed line integral we will go anti-clockwise this way. Then according to my right hand rule, this right hand rule, thumb will give me the direction of area vector. So if I am going anti-clockwise in evaluating this right hand side of the theorem, closed line integral, then area vector is to be taken along positive x, right? Because of that right hand rule. Remember that. Now we will solve this. Now my solution starts like this. First of all, I will write the theorem. You know that first I have to calculate the curl. curl of V. I have given you the formula. I'm writing directly the answer. When you calculate the curl of V, it will turn out to be 4 z square minus 2x I cap plus 2z k cap. You will use the determinant formula given vector field and solve for the curl of V. It will turn out to be 4z square minus 2x I cap plus 2z k cap. So this curl has x component and z component, right? Is my curl, and my area vector dA is dy dz I cap. Why so? Because this area lies in yz plane. That's why dy and dz. And area vector is to be taken along positive x. Positive x means I cap will be here. Now again, x is 0 for this surface because it is placed in yz plane. X is 0. So I write since x is 0, left hand side of the theorem, that is curl of V dot dA will be 0 to 1, 0 to 1, 0 to 1, 4 z square dy dz. How? See, I have to dot curl of V with the dA. dA has x component. What is the x component of curl of V? X component of curl of V is 4z square minus 2x. So actually it will be 4z square minus 2x dy dz. The limits will be 0 to 1 on y and z, because my area goes along y 0 to 1. I have to move from 0 to 1 to reach here, then 0 to 1 along z to reach here to make up this area, right? Now since x is equal to 0, this term goes 0. So only remains 4z square dy dz in the integral. And when you calculate this integral, it will turn out to be 4 by 3. So this is my left hand side. My left hand side for the Stokes theorem. Now move to right hand side. Now in right hand side, I have to find the line integral, closed line integral. This thing, right? My perimeter is square. My perimeter is square. Now I divide this perimeter square into 4 line segments, 4 displacements. This one I name first, this one I name second, now this one I name third, and this one I name fourth. So I will first find V dot dl for this, then this, then this, then this, and add those 4 pieces to get the value of the closed line integral, right? So for first piece, x is 0, z is 0, and V dot dl is equal to 3y square dy. Why so? x0, z0. Move to the figure. For this piece, x is 0 because x is 0 for all the pieces. For this particular piece, x is 0 because x is perpendicular to YZ plane. This line lies in the YZ plane. So x is 0. Z is also 0 because you are moving along Y direction here. Along this line, the Z coordinate is 0. So x is 0, Z is 0. That's clear, right? Then we have to do V dot dl. dl is infinitesimal displacement vector. It is normally dxi cap plus dy j cap plus dz k cap. But I am going along y direction, so it has only y component. I have to dot that with y component of v vector field. Y component of vector field is 4yz square. No, sorry. Y component of vector field is 2xz plus 3y squared. Now since x is 0, this term will vanish. Only 3y squared will remain in the integral. That's where I have 3y squared dy. And when I integrate it, v dot dl will be 0 to 1 limits of integration because I am moving from origin to coordinate 1 along y direction. 3y square dy, which is equal to 1. So for first piece, my v dot dl is integral v dot dl is 1. And similarly, for second piece, you chuck it at your places. X is equal to 0, y is equal to 1. My v dot dl will be 4z square dz. And when I integrate v dot dl, it will be 0 to 1 4z square dz, which will be 4 by 3. Check all these integrals. X is equal to 0, y is equal to 1 for second piece. X is equal to 0 for all pieces, y is equal to 1. Because here y coordinate is 1 for this piece, right? Then I am moving along z direction. So dl will have only z component, and z component of v is 4yz square, right? 4yz square. 4yz square. Now it only in the integral it remains 4z square because y is 1, right? Then evaluating this integral will yield 4 by 3. Come on, move. Then third piece. For third piece, x is 0, y is 0. V dot dl is 0, right? So integral v dot dl sorry, it is for fourth. For third piece, let me clear it. For third piece, x is equal to 0, z is equal to 1. V dot dl is equal to 3y square dy. Then integral v dot dl is equal to 1 to 0, 3y square dy, which is minus 1. Let me check this. First third piece, x0, z1. x0, z1. See, this third which x is 0, z is 1 here, right? This first thing. And I am moving along y direction. Therefore, my displacement will have only y component. And y component of v is 2xz plus 3y squared. Now, since x is 0, this term will vanish. Only I will have in the integral 3y squared. And on y, limit will be 1 to 0. So this is the expression 1 to 0, 3y squared dy v dot dl x equal 0, z is equal to 1. So you check it, it will be minus 1. Now next, fourth piece. X is equal to 0, y is equal to 0, v dot dl is equal to 0, integral v dot dl is equal to 1 to 0, 0 dz, which is 0. See how x is equal to 0, y is equal to 0. For fourth piece, go to the diagram. For fourth piece is this. X is 0 and it was y is 0. Y is also 0, right? And you are moving along z direction. So your displacement will have only z component, dz. Z component of v is this, but since y is 0, this will vanish, right? Limit will be from 1 to 0. So x0, y0, v dot dl 0, integral from 1 to 0, but since integrand is 0, it is 0. So closed integral v dot dl, that means my right hand side of Stoke's theorem, I will have to add these four pieces. 1 plus 4 by 3 minus 1 plus 0. Adding these, you get 4 by 3. Right? 1 plus 4 by 3 minus 1, 0 is 4 by 3. C. This is the value of right hand side. 4 by 3. Right? 4 by 3. C. 4 by 3 was our left hand side. This is my left hand side. 4 by 3. So hence LHS is equal to RHS. Theorem is verified, right? I will give next topic as our, this finishes our theorem. Electrostatics. What's electrostatics? It is actually study of charges which are either at rest or moving slowly. So when we say we are studying electrostatics, that means we are studying the properties of charges which are either at rest or moving slowly so that their motion can be ignored. Next thing, I will give introduction of this. These things Charges are of two kinds, namely positive and negative. This thing you also know. Now you also know like charges repel, unlike charges attract, right? Another thing, properties of electric charge. All these things you have done in your 12th class. I'm revising them. Now, charge has three properties. First property is called additivity. Additivity. What is the meaning of that? Meaning of that is, for example, if you take sodium atom, its atomic number Z is 11. That means in its nucleus, the model of atom, you have a nucleus, positively charged nucleus, then you have extra nuclear part. In its nucleus, there are 11 protons, and in extra nuclear part, there are electrons, 11 electrons. The additivity property says if you have to find the charge of a body, you algebraically add all the elementary charges in it to get the charge of the body. For example, if I have to get the charge of this sodium atom, I have to take charge of 11 protons and add the charge of 11 electrons. Algebraically means when you add, take positive charge as positive in the addition and negative charge as negative. So it has one proton has plus E charge, one electron has minus E charge. So total charge in this sodium atom is plus 11E minus 11E, which is 0. So it is neutral, right? 11E minus 11. E stands for this value 1.602 into 10 raised power minus 19 coulomb. This is additivity property. Then second property is charge is conserved. Conservation, right? That means total charge in the universe is constant. That means if some charge appears somewhere, same amount must disappear somewhere else because total is conserved. I will give two examples here. One is if a gamma ray photon annihilates, it's not annihilation, gamma ray photon disappears, we get electron and positron. What is this gamma ray photon? This process is called pair production because a pair of particles is produced. Now see, it obeys the conservation of charge. Left hand side, photon is neutral, so you have zero charge. On right hand side of this process, you have also zero charge because electron has minus C, proton is positron, it's positron here, positively charged electron. It has plus C, total charge 0, here total charge 0. Now second example I will give for conservation. This process is called pair annihilation. This pair production, it is pair annihilation. Here electron and positron combine and we get a pair of two gamma ray photons. Now again, Q is 0 on left side, Q is 0 on right hand side. So every uh, process obeys this conservation of electric charge principle, right? Now, this all for today. Thank you. You work hard. God bless you.